In this video, let's talk about the derivative of any based logarithm function, as we already know the derivative of the natural log function. So recently in class, we looked at the derivative of the log base e, or the natural log function, which we determined to be 1 over x by differentiating implicitly. And essentially, for determining the log of any base of x, we can find its derivative doing exactly the same strategy. And I just recorded this entire video for about 10 minutes, but it appears as though I forgot to press the record button. So now I'm pretty agitated and annoyed, but you can see my writing's already here. So instead of rewriting it, let's just go through what I wrote instead of doing it all again. But basically what I did is exactly like we did with the natural log. I changed f of x to y because those usually mean the same thing. And then I applied the definition of the logarithm, which, we can always interchange the role of x and y and change it from a log to base a function. And from there, we can differentiate implicitly, taking the derivative of both sides. The derivative of x is just 1, and the derivative of any base exponential, well, we just covered that in the last video and in class previously, but the derivative of any base exponential is the same exact thing, a to the y, multiplied by the natural log of the base. So in order to do this derivative, well, it's exactly itself times the natural log of the base. But also, since this derivative does not match the variable within, as if we're differentiating implicitly and we get a mismatch in our variables, we need to also multiply by the derivative inside. So since y and x are defined implicitly, derivative of y with respect to x needs to come out as well by the chain rule. And ln of a kind of also popped out as a multiplier. Similarly, really, you could think about it as being due to the chain rule, or just by remembering that derivative of a to the y. Anyways, as we usually do with implicit differentiation, we could then solve for dy dx by dividing both sides by a to the y ln a. And that would leave us with this. And, again, exactly as we did with the natural log function, a to the y is equal to x. So we could substitute that in and find our derivative of our logarithmic function base a. And what it turns out is the derivative of log of any base of x is just equal to 1 over x, well, times ln a, but technically it's 1 divided by x and also divided by the natural log of a. So it's very, very similar to that of the natural log function, whose derivative is 1 over x. But essentially, we need to multiply by ln a as well to sort of compensate for being a base other than e. Now, another way of doing this, and this is actually a much simpler way of figuring out the derivative, is instead of using implicit differentiation, we could instead just use the change of base formula for a logarithm. And we talked about this briefly at the end of class Monday. But remember that if a log of any base can always be written using any other base by using what's called the change of base formula. So if our logarithm of x is base b, we could rewrite that as log of x divided by log of b, where we can choose any base we want for that value and it will remain consistent. Like with the log base 2 of 7, I could rewrite that as ln 7 over ln 2. And that's exactly what I did right here. I took log base a of x and rewrote it as ln x divided by ln a, because a logarithm of any base can be written as a ratio of 2 logarithms of any base. And, the base goes on bottom is another way to remember where does the base go. But essentially, well, why is the change of base formula helpful for this function? Well, if I'm trying to solve the derivative, I could then take the derivative of this instead if I'm trying to figure out what this is, because we already know the derivative of ln of x is 1 over x. Also, since ln a is a constant based on whatever the base is, we could factor that through ddx instead, and we then know, the derivative of ln x is just 1 over x. And essentially, we see 1 over x divided by ln a, and what we end up with is 1 over ln a times 1 over x. And, or again, because fractions multiply, 1 times 1 is 1, and ln a times x is x. Notice I get the same answer. So I was just trying to show you guys, well, there's more than one way to figure out this derivative, but in summary, the derivative of any based logarithm is 1 over x multiplied by ln a, or really it's divided by ln a, but it's 1 all divided by x times ln a. It's very similar to the rules for general exponentials. And so actually, let's go down to the bottom of our worksheet just to sort of fill this in. But essentially, the most important thing to remember in a calculus course from chapter 4 on exponentials and logs are, what are the derivatives of these functions? Because, we have exponentials, we have logs, and there's 4 different categories here. And now essentially we've solved all of these derivatives as we wrap up this particular chapter. But so how I remember it is, well, e to the x, it's a very fundamental, important function in calculus. It's the only function whose derivative is exactly itself, or is the original function, e to the x as well. ln of x, again, base e is special. When you have ln base e, or a logarithm base e, which is represented by the natural ln, is we just get 1 over x. It's kind of like a simple format, the reciprocal function. And these two things, you want to really memorize these as the derivatives of the foundational elements of exponentials and logs. Now, if we want to do it for any base and it's not base e, it's almost the same, no pun intended. It's basically the same thing. You just need to adjust by the base. And so what I say is, well, if we want to change it to base a, the derivative is still itself, but it's also multiplied by ln a. Again, and we rationalize this a couple ways, by the difference quotient, or it's also technically by the chain rule. But essentially, you just need to multiply by this value in order to adjust the derivative for being any base other than e. And if it is base e, this formula still holds. So technically, this is the same formula. This is just the general case rather than the specific case. Similarly, if we want log of any base, we can adjust the formula in exactly the same way. Instead of multiplying by ln a, we're dividing by ln of a, and we get our derivative of log base a of x. It's 1 over x times ln of a. For some reason, I don't know why that dot appeared twice, but nonetheless, it's almost the same. And for me, that makes it very easy to remember these derivatives, that when I change the base, all I need to do is take the natural log of the base, and either multiply for derivatives, divide for logarithms. And again, you could think about it as either using the chain rule or as using the change your base formula. In terms of, again, if you're wondering why, well, it's a little bit more complicated as to why when we're taking any base. But again, the simplest cases, those are the keys. Those are the most important ones, because if you know those, you can figure out another base using algebra or formulas such as the change of base formula. Anyways, in the next video, let's look at some examples, and then we will also get into solving equations involving exponentials and logarithms, which is a review, but something else that I wanted to sort of show you guys how I do it, because it's not the same. I have my own way of doing it. And anyways, see you in the next video.